Alright, so today we're going to be doing 4.15, which is piecewise functions, and we're going to be specifically talking about nonlinear piecewise functions today. So what that means is piecewise functions that are comprised of both linear and nonlinear functions. So it's not just limited to linear functions. Why is my, oh, it is connected. I don't know, it's saying it's not connected and it works fine. Okay. So just before we get started, we're going to refresh how we deal with these types of functions, how we graph them. So I'm just going to quickly review that with you. So to graph a linear function, you're first going to start with the y-intercept, which in this case is at -1. And then you use the slope, rise over run, down 2/3. And then if you can't keep going, you can also go to the left, up 2/3. So that is how you graph a linear function. So does everyone in here feel comfortable with graphing a linear function? Okay. Now we're going to talk about an absolute value function. So for an absolute value function, if you remember, the standard form of an absolute value function is f of x is equal to a times the absolute value of x minus h plus k. So once you know the standard form, you can actually take out the vertex h and k. Now what's going to happen to your h when you take it out? Good. Flip signs. What's the k going to be?
-3.
The h is -3, the k is
2.
2. So you're going to plot at -3, 2. Now absolute value functions are always a v or an upside down v. If it's upside down, the a value will be negative. In this case, is it an upside down v?
Yeah.
Yes, it is. So the a acts as a slope, okay, and you always go to the right. So we're going to go down 1 over 1. Down 1 over 1. And you're going to repeat this process until you can't anymore because you run out of room. And now we're going to talk about how the rest of this function is graphed, where the other half of the v is. So, absolute value functions have symmetry over the axis of symmetry. Now, how did I know the axis of symmetry was in this spot? Exactly, it has to go through the vertex. So my function has to have symmetry over this. So what other point would I graph on this side over here? Good, and? Good. Once you have that, you can now connect them into a line. You're going to put arrowheads on both ends because it is infinite. So any questions about how we graph the absolute value function? And then the last one we're going to talk about is quadratic. Anybody know what this form is called that the quadratic is in?
Vertex form.
Good, vertex form. I wrote out standard vertex form for you here. So what is the vertex of this quadratic?
+2, -1.
Good, +2, -1. And do you remember the 1-3-5 rule I taught you yesterday with graphing these? So I'm going to put in my axis of symmetry, which goes through the vertex. Oh, I had it so good and then I messed it up. There we go. Here's my axis of symmetry, which is at x equals 2. So here's the 1-3-5 trick with quadratics. First you determine, is the a value 1 here? So we can go up 1 over 1 on the right. And then from there you go up 1 over 1, up 1, 2, 3 over 1, and then you could then go 5 and 7. Now if you don't like the tricks, you can also use table graphing. Make a table, plug the values in as well. Now your graph has to have symmetry over the axis of symmetry, so we map it on the other side to match. And then once we have the whole thing, we just connect it. And if you're still struggling with graphing, you can always use Desmos to check your work. and Desmos will tell you if you're right or wrong. So, does anyone have any questions about any of the graphs so far? Okay. Now we're going to talk about how we evaluate piecewise functions. So, do you remember this?
Yeah.
Okay. So, how this works is each one of these is a boundary, and that tells us which function we plug into, okay? So, we look at the value that we're trying to evaluate, -1. Which of these three boundaries does -1 fall in?
The middle one.
The middle one. Does everyone see why this falls in this boundary right here? Because -1 is between those two numbers, right? Okay. So, once you identify that, that is the function you need to plug that value into. So I like to put a -1 instead of just the -x. That's just me. If you don't want to do that, you don't have to. And then I just need to evaluate that. What is -1 times -1 times -1?
Positive one. Oh, negative.
-1, good. -1 times -1 is? 1. 1 minus 3 is?
-2.
Good.
Is it plus 3?
No, because I had to multiply it by the -1. Alright, next one. What boundary does 5 fall in?
The bottom one.
The bottom one. Why couldn't it fall in the one above it?
Because it's got.
Very good. The inequality sign says x has to be strictly less than 5. So for that reason, since 5 is included, I have to use the one with the equal to underneath it. Does everyone understand why we have to use the one in the pink? Okay. So, from there, we're going to take that function and plug it in. Plug in x. Does anyone remember what those bars are called?
Absolute value.
Good.
So that it's impossible to be negative.
Yes. So within it, whatever comes out will come out positive. So what's 5 minus 8?
-3.
What's -3 taking the absolute value of?
3.
And then it's made negative again because of the negative on the outside. It was positive for a minute and then it went back to negative, but that's how it goes. So I want you to look really carefully at this one. -2.5. What boundary does that one fall in? Is -2.
Oh, it does say the middle one.
Is -2.5 greater than -2?
No.
Does it fall in any boundary at all?
No.
This is what we call undefined.
I never realized that.
Undefined. So this is what we would call a discontinuous. Piecewise function. Discontinuous piecewise function. Because see how we left off at -3 and then it doesn't pick back up at -3 right here? It has to pick up where the other one leaves off for the boundaries. See how here the 5 picks up where the 5 left off? That part of it is continuous. It's the other part that is not continuous that makes the whole thing discontinuous. And we'll talk more about that as we go through the lesson. How's everyone feel about this one? You ready to graph one?
Yeah.
Alright. So I am going to warn you ahead of time here that for the purpose of education, I am going to be erasing stuff and drawing stuff and erasing stuff. So if you're not using pencil, you might want to wait a few minutes before you write anything out, because if you're using pen, I'm going to be like showing you stuff and then erasing the part that we don't need, just for the understanding purposes. So I just want to let you know that. So what kind of function is this right here? Linear, quadratic, absolute value, constant.
Quadratic.
This is quadratic. And it's quadratic in standard form, right? But we could easily convert it to vertex form by doing this. Does everyone see why it's okay to do x minus 0 and it doesn't change anything? Like if you have a number and you subtract 0 from it, does it change the number? No. Does anybody know why I would write it this way? What's the reason? How does it help us? Don't I now know what h and k are?
Oh, yeah.
You see it? What is h?
You get the first piece.
Yes. 0, negative 6. So does everyone understand why I added that 0 in there? You know what vertex form looks like? Yeah. Oh, yeah, this part. It's just when I go to graph that I'm going to be erasing stuff. So you remember this form for quadratics? I wanted to make this have that form. I saw that in the parentheses it's missing the minus k. Does that make more sense now? Okay. So the vertex is at 0, negative 6. So this point you can plot, whether you're using pen or pencil. Okay, I'll tell you which ones not to do. So let's talk about how we graph a quadratic. Remember the 1, 3, 5 rule? So if this is my vertex, then this is my what?
Axis of symmetry.
Good. It's my axis of symmetry. So it's symmetric on those both sides, right? In a normal circumstance. So I would go up 1 over 1, and I have a point here. And then it's symmetric, I also have a point over here. We would then go up 3 over 1. You can plot these. These are okay to plot. Now, here's where I want to be careful. What does the boundary tell me right here? Good. So, see how right here, these are all the values over here in this pink region that are less than or equal to 2. Everyone see that? So can my graph go into the white region? No, it has to stay in the pink, right? So normally you would continue with your quadratic, but we can't do that. So the points, like if I were to keep going over here and graphing it, I don't want those points on my graph, but I do have to finish the other side of my graph. So we would have a point here, and we also have a point 1, 2, 3, 4, 5 over 1. And then we'd have a point 1, 2, 3, 4, 5, 6, 7 over 1. So this is the piece of my quadratic I'm looking at. Now, piecewise functions are like taking little snips of different functions. So like if you were to like make a collage and I gave you a bunch of functions and you cut pieces out of different functions and put them on one graph. That's how your absolute value or your piecewise function is going to look. So does everyone understand why we stopped at the 2? Okay. Now we're going to move on to this one. So, and you can write this, by the way, if you want. So this is y equals 4. So y equals 4, what kind of line is that?
That's a horizontal line.
It's a horizontal line. But where does my horizontal line exist from? What two values?
2 and 5.
Good. At 2, it's going to be a what kind of circle?
Open.
Open. Do you remember this a little bit now?
Yeah.
So it's an open circle at the 2. Why is it an open circle at the 2?
Because it isn't got the line. It isn't got the line in the
Very good. When you have this symbol right here means open circle goes there, okay? And then the next one. And I won't do the erasing thing, so you can go ahead and write. I just figured I would show you with the shading instead of the erasing. It worked out better that way. So, what kind of function is this one right here in the green?
I have a question.
Yeah.
Why does the y equals 4 line not keep going past the 5?
Look at the boundary that it exists on.
It goes up to the boundary.
Does that make sense?
Yeah.
So, this is a linear equation. It has a slope and a
Curve.
y,
Y-intercept.
right? Isn't this in the form, you remember your old friend mx plus b? You see that? So b tells me where we start on the y-axis. But the problem is the y-axis is way over here. My graph's not supposed to start until we get to what value? 5. So my graph's going to start in this region right here. So let me make this pen bigger so I'm not here all day. This region right here is where this graph exists, okay? This graph exists in the pink, and this one exists on the blue. Does that make a little more sense with the color coding? Okay. So the problem is I can't start on the y-axis like I normally would. So what I'm going to do is I'm basically going to ghost graph, okay? So I'm going to start down here, normally like I would start here, and I'm going to go up 2 and over 1. But I'm not going to actually plot it until I get to where I need to be. But it just shows me where the points are. Up 1, 2, over 1. 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 I have a point here. Is that point open or closed?
Open.
Open, because of the inequality sign right here, right? And then I continue, up 2 over 1. But now my graph actually exists, right? So now I can actually put the points down. Does that make sense? So these graphs all exist on their own, but we're just taking little pieces of them and putting them all on one graph. Okay? So here's the important part. Domain and range. Because these are the kind of questions I would ask you on a quiz and test, right? You know that I don't ask you to graph. Typically you have to evaluate graphs. So let's talk about what a domain is. A domain is all the possible what that a function takes.
X and fixed value.
X values. So when I think of what this graph is doing, is it going out wider and wider as it goes on? What do you think? Yes, it is, right? It's going wider and wider and wider, right? So eventually, isn't it going to go to negative infinity over here?
Yeah.
Yes. Good. Over here, it's going up forever, but it's still going out wider and wider, meaning it's going to go to what in this direction?
Positive.
Positive infinity. Now here's the tricky part with piecewise functions. We have to make sure every x that left off picked up on another x. So see how right here, the 2 we left off at 2, but we picked up there and then continued. So you're going to notice that on top of each other, there's going to be these open and closed circles. Think of it as if you squish the graph together. Those would overlap on each other, and this would all become one big piece, right? So as long as they pick up where the other one leaves off, your domain doesn't have any holes in it, okay? Because we're still taking on every x value. Think of it as like a tag team race. You left off at 2, your friend's picking up at 2. You left off at 5, your friend's going to pick up at the 5. So there's no gaps. So we're good on our domain. Now range can also have gaps as well. So I'll talk a little bit about that. This one doesn't have any though. So the domain is from negative infinity to positive infinity. Now as for your range, what's the lowest that this function will ever go? Good. Yours is sideways. It's really hard for me to write that way on here, so I'm just going to write it the right way. We're going to go from -6, and do you see how I used that square bracket? Why did I use that?
Because it stops there.
Yeah, because it's actually included in that value. There's no open circles to worry about at that point. Now from here, see how we don't care about what this side is doing? Because this part alone, this blue graph carries the weight of the whole thing right now, up to the range. It's going to take on every value in the range just based on the blue graph alone, right? Because that one's going up forever. So we don't even have to worry about this one filling up any of those holes, because range is going to be from bottom to top. This graph's going to go on forever upward. No holes in it. So for that reason, it's going to positive infinity. So it's one of those things that's like very visual to understand. So do we have any questions about that one?
So those little gaps on the right side, those don't mean anything because you have the blue graph that's completely enough.
Exactly, yeah, because range only cares about the y values. One of those several pieces of the function is going to at least at some point pick up every single one of those y's. So we're going to skip 2 because it's a little fractiony, and we don't want to do that today. So we'll skip number 2. You don't have to do number 2. And I forgot we were on the wellness when I planned this, so we don't have as much time. So let's go ahead and try number 3. So if it helps you, we can also highlight the parts of the graph that your graph's going to fall in right in the beginning. So I don't know, I think it's kind of helpful. So this graph right here, we know is going to exist when x is less than -2. So it's going to exist, let me make it a little nicer, like over here. And then this graph right here is going to exist from -2 to 1. I gotta make my my pen smaller. It's like too thick at this point. So you don't have to do this part. I'm just trying to help you understand the boundaries, how the boundaries work. And then this graph right here exists when the values are greater than 2. Alright, so now we'll go ahead and graph our functions. And you can see we're going to have a discontinuity, right? Everybody see how we already know that from just the shading alone? Okay. So, what kind of function is this first one right here? Good. What's the vertex of it?
-3, -5.
Good. So -3, -5 down here. What's the a term of this quadratic?
1.
Good. The a term, for anyone who's wondering, is the coefficient in front of that. So we're going to go up 1 over 1. But here, why am I going to put an open circle right here?
Because that's where the shading stops.
Yeah, and it has a boundary right here. And as you can see, the boundary that exists doesn't have an equal sign in it, so I don't include that point. And then my quadratic is going to mirror over this line because this line is the invisible axis of symmetry. So we also have a point over here. Now that point is included because -4 is in fact strictly less than -2. And then we can continue. So we go up 1, 2, 3 over 1. Up 1, 2, 3, 4, 5 over 1. And that's about all we can do for this graph because we can't really go any more. So we connect it and we put an arrowhead on it. Now for the next one, -1, that's just the graph of a horizontal
line.
Good. And that horizontal line only goes from -2, where it is included, to 1. And then lastly, what kind of function is this? Good. And its vertex is 4, 4, 4, 4. And is my a value negative or positive? So its slope is -1. See that negative sign in front? So it's going to go down 1 over 1. And then it has symmetry over this invisible axis of symmetry, which goes through the vertex, so it's going to match it on this side. Why did I use the open circle?
Because the boundary is there and it's not a
Good. Does that make sense? The setup of the graph so far? Alright. Does the shading with the colors help understand the boundaries?
Yeah.
Okay. So this might also help you with your domain. So your domain can only be -infinity to +infinity if there's no gaps. But clearly here we can see we have a gap, right? So what's my graph doing? It's going from -infinity. So over here it exists because of this arrow going up, outward. And then my graph keeps going until it gets to what? Where does the end of the boundary start here? 1. So the domain goes okay from those values. And then union, that means also. The graph then goes from 2 to what?
Positive infinity.
Good. So see how we had to leave out that portion right there? That white non-shaded portion?
Yeah.
Okay. So the range can also have the same kind of behavior. And I just want to point out also, I use the curved brackets at the 1 and the 2 because of the open circles. So let's talk about the range. This can be a little tricky for people. Range is the lowest that the function. Thank you. The lowest that the function goes to the highest that the function goes. Now this looks like the lowest point of the function, but what do you notice over here?
Keeps going to negative infinity.
It goes to negative infinity. So the blue didn't help us go to negative infinity, but the green did. It helped us go down to negative infinity, right? And then did one of the functions help us go to positive infinity?
Yeah. Yeah.
Which one?
Blue one.
The blue one, right? And in between, we don't have to worry about any discontinuities because you see how from here the blue picks up and it takes on all of those y values in between. Therefore, we don't have to worry about anything being left out in the middle. So my range is from negative infinity to positive infinity here. Like the graphs basically come together to make that possible here in this one. All right, does it make sense? Ish. So now we're going to work backwards. We're going to determine the equation that would match the graph. So if it helps, you can do your shading here to see where the boundaries are. You see those two boundaries right there? So we know we're going to have some form of discontinuity, right? So I like to do the boundaries first. Oops, that's not what I meant to do. Hang on. Undo. I want the highlighter. There it is. This is going to be the graph that goes with the yellow. And this one is going to go with the pink, just so you can kind of color code and see what I'm doing there. So, what boundary does this have? X is less than or equal to what value on the x?
1.
Negative 1.
Negative 1.
Everyone see how we determine that? Okay. What boundary does the other one have over here?
0.
X is greater than 0. These are always based on x. If that helps you, okay? So, what kind of function is this one? Linear, quadratic, absolute value, constant?
Linear.
Linear. So to come up with the equation for a linear function, we got the formula y equals mx plus b. What does the m represent?
Slope.
Good. Can we find the slope of this by counting rise over run?
Yes.
So we go down to 1 over how many?
2.
Over 2. Which means my slope is negative 1/2 x. And then, what's the problem with finding the y-intercept? Do we have one in our picture? Does this graph cross the y-axis, the one that's linear? Is it crossing this axis right here?
No.
No. But can't we figure out where it would have crossed it if it kept going?
Go down 1, go over 2.
Exactly. We could go down 1 over 2 to figure out where it would have crossed. And it would have crossed at what value?
2.
So you see how it's kind of like if somebody takes a picture of you, but it's only like your face. It doesn't mean that you didn't have shoes on just because they're not in the picture. This doesn't mean it doesn't have a y-intercept just because it wasn't in the picture that we were looking at, right? It still has it, it's just not in the picture we were looking at. Now we're going to do the quadratic. So, I want you to keep in mind the graph is a little bit weird. It's like going by 0.5s, so don't let that confuse you, okay? What is the vertex of this? What's the vertex? Good. 2, -3. From there, we went to this value. So we went up 1, over 1. Is that following the 1, 3, 5 pattern? And then here we went up 3, right? So it's following the 1, 3, 5 pattern that we talked about, meaning my A value has to be what? 1. So, vertex form for a quadratic is this. You remember this? All we need to come up with that equation is A, H, and K. Do we have those 3 items? Yes. So my formula is 1 parenthesis x minus 2 squared plus or minus k. You don't need to put the 1 there. 1's not necessary. I just put it to help you understand where it came from. Okay? So do we have any questions about number 4? And remember, you always have Desmos to help you check your graphs, right? At least the portions, and make sure they're good. All right. So here's a little story about functions. So in the normal function world, functions are continuous when the graph is a single unbroken curve that you can draw without lifting your pen from the paper. So that's what makes a normal function continuous. So if you look at these 2 pictures, which of these 2 functions is continuous, f or g?
F.
Good. And why is g not a continuous function?
It's got that dot.
Yeah, it has a point that goes off the chart, right? So, for that reason, g is not a continuous function, but it is still a function because it passes the vertical.
Line test.
Yeah, it would still pass the vertical line test. So that's the rule for normal functions. Now piecewise functions have more lenient rules, because don't all piecewise functions look like this? They always have things that are pieces that are off. So if we just were going to be simple about it, we would say all piecewise functions are discontinuous. They all are. But we can have our own rules within the world of piecewise functions that make them piecewise continuous. So let me talk a little bit about that. A piecewise function is piecewise continuous if each boundary picks up where each boundary leaves off. See how here at 0 this one picks up at 0? And see how here this one picks up at 3 where this one leaves off? That means that they are piecewise continuous. Does that make sense? Does this boundary pick up where the other boundary left off? It's also piecewise continuous. Not to be confused with regular continuous. Is there an example we did today that would be not piecewise continuous?
Yeah. The number 4 as well.
Yeah, number 3 and number 4, right? So on your homework tonight, you can do all the problems except number 3. You don't have to do number 3. That just cuts down the workload a little bit. So you have a good amount of time to work, maybe. Let me see, I don't remember. I forget the wellness